Okay, cool, thank you. So who of you have ever felt an earthquake before? And who has seen really damage of buildings? You. And how many? Many? Okay. So this is how it can look like. That was Tokyo in 1923 after the big Kanto earthquake. And obviously we are dealing with a lot of communities that are under risk of earthquakes, also of other natural hazards. And the question always is, what are the effects that earthquakes have to a community, and what can a community do to mitigate these effects? So first I want to give you a quick tour about what earthquakes are. And the earthquake science started basically in San Francisco in 1906, and that had a very particular reason. Luckily, I think even months before the earthquake, there was a big geodetic survey around the city of San Francisco. And the geologists and researchers were then, after the earthquake, repeating this very survey and understood that earthquakes actually occur along these structures that were at that time not yet called faults, but kind of lines. And the point that they made them sure that this thing happened here is that fences or other structures were kind of shifted, and they saw that along these lines there's this motion that then generates all the earthquake waves. And this is the motion of one earthquake at this San Francisco 1906. And then if you wait for 1 million years, then a little creek gets bent maybe even 100 meters by side. This is the very same effect as you have there. So, do you want to sit there? Yes, please. Very lovely, thank you. So, at some point, the community thought, we understand how earthquakes work. There are these, what we call faults. These are the locations where earthquakes are. And everything seemed to be fine, but then unfortunately, earthquakes do not know these maps. They don't understand to read the maps, so they happen somewhere else. And this is an example, 1995 in Kobe. There was a known fault, but the earthquake ruptured further north of that fault into the city of Kobe and destroyed up to 100,000 buildings, I think, were destroyed in Kobe. And this was triggering the Japanese government to kind of redesign the building codes and start rebuilding the city according to earthquake safety standards. In 1989, we had a big earthquake in San Francisco, and I'm highlighting this because it points out a very different aspect of earthquakes. This is not just the earthquake itself where it happens, it's actually the effects of the earthquake on the ground far away from the fault. And what happened there is we had an earthquake, I don't want to say similar to the 1906, but along the San Andreas Fault, so that was all known, nothing particular about this here. But what happened was that in this district, this is the Oakland area, this two-level, you can hardly see, but it actually has two-level freeway collapsed. And we had another effects in the Marina district, in the northern part of downtown San Francisco, where also a lot of buildings were destroyed. The reason was that we were talking here about site conditions. Depending on the underground, the level of shaking that comes from the earthquake and reaches these points can be amplified. And this is what happened in San Francisco. The areas that were mostly destroyed were so-called unconsolidated sediments. And these were the areas where the rubble of the 1906 earthquake was dumped to create sort of new land in the sea. So it's in a way the damage of the 1989 earthquake in San Francisco was sort of an echo of the 1906 earthquake. So the important thing here is we have different types of undergrounds. We have hard rocks where the shaking is not amplified. We have these unconsolidated sediments. This is like sand and stuff that basically shakes like a pudding after it gets excited by the earthquake waves. And we can even have liquefaction, which is unconsolidated sediments, but with a lot of water in there, and then this sand under shaking all of a sudden appears to behave like a liquid. So taking this into account and the locations of earthquake, we actually create an earthquake hazard map. And this hazard map basically tells you what kind of shaking levels, maximum shaking levels, would you expect in, say, 50 years, roughly, and at which probability. The only problem is, I mean, we can read the map in the sense of red is probably dangerous and orange maybe not so much, but what does it really mean? So we have to actually look into the risk. And the risk means we are combining the hazard, which is the shaking of the ground, with the exposure, which is a description of what kind of buildings or assets we have in the world or in the country or in the city. And each of these buildings have a related vulnerability or fragility, which means how do they react to the shaking. And all of this together is the risk. And so this is usually done in a sort of very static way. You kind of do a survey, you figure out how many buildings of what type you have, and you say, okay, let's say our city has 10% of one type of buildings, 12% of another, etc. And that's all you know. But the problem is we have a lot of dynamic effects in the building environment. We have dynamic exposure because we have urbanization, we have changing of buildings. Buildings are taken down, rebuilt, maybe retrofitted. And we have dynamic vulnerabilities, which means also a building can change its vulnerability, but also there is an overall city vulnerability. Cities do not scale. You cannot just double the size and the escape routes are all the same. It doesn't work. So we have dynamic risks. And to able to really communicate what's going on, the risk, we need to monitor the exposure so that we can monitor the risk. So our idea to handle this was, we got to look at the buildings. The buildings are the key, and we want to know every building. We want to know where it is, how big it is, how many people fit in there and will be in there, what is its value and what is its type. And there are further aspects of the dynamics. As I said, it's the growth of the city, it's the modernization, but it's also a time dependence in terms of already achieved damage states of a particular building. You can have a big earthquake that creates a particular damage state, and then you have following aftershocks that are actually weaker, but they already hit a damaged building. So you cannot assume that this every building in the aftershocks is undamaged and thus will not collapse or anything. Quite the contrary, we see a lot of buildings that are collapsing in aftershocks, although they were withstanding the main shock. So the challenge for what we were trying to do is a dynamic model that should capture everything that's going on, and we want it to be a high resolution. We want to understand every building that there is on Earth. So the strategy, obviously, we don't have enough engineers in the team that we could send them to every building, so we decided we have to do something completely different. We do so, we're building everything around the OpenStreetMap ecosystem. So we take the buildings from OpenStreetMap and we merge them in a data integration process with these classical exposure models that explain what kind of types we have in a particular city. And for each building separately, we try to figure out what it is. And this is all done in a rule-based processing system, which I will explain in a minute. But of course, our exposure model starts with any other model. It's a blank area. The world is blank. We need to populate it with buildings. To do so, we start with the built area. We first want to know, where do we have to expect buildings? Because we all know OpenStreetMap is not complete and we cannot just rely on only the buildings that are in OpenStreetMap. To do so, we put a grid on the world and we use the global human settlement layer on a quad-tree level 18 tile grid, roughly 100 meters in this hemisphere. And we projected every global human settlement layer data, these pixels, onto these tiles. We do this in a geometric processing, so we have the polygons of each of these tiles. So we know in which tile in the world we have to expect buildings. Then we put the buildings on top, and then what you can already see is this seems to be pretty complete. We'll have more or less all the buildings that are expected to be there. Well, here's obviously buildings missing. And so what we do, and this is a completeness assessment, so we know in these tiles we have all the buildings, in the other ones we have to substitute and make sure that we account for the buildings that are missing. How we do this, cliffhanger, will be in the next talk after Matthias' talk. So as soon as we have the buildings and the tiles, we have to process them, do a lot of stuff, and we use our Robotnik rule-based processing engine. So any building that changes in OpenStreetMap comes into our engine, into a queue, is going to be processed according to rules. And this engine is distributing these atomic tasks onto many different processes. So what are rules? Let's imagine you have this little funny eatery here in Tokyo. And this is a data set in OpenStreetMap. So what we know from OpenStreetMap, we can figure out what the occupancy is if somebody has put in a POI. So in this case, it would be some sort of a fast food store or restaurant. In a way, some commercial entity. We have the footprint, which means we know exactly where it is. So this is at this corner here. And we know the footprint size. And then if we have the number of stories given, then we can estimate the floor space, which tells us how many people are there. And given that we know the occupancy type, we also know that at what time of the day we have to expect some people there. If it's a residential home, then at the night people will be in there. If it's, but during the day it's not so populated. We can look at the position. This is important for earthquake. Is it detached or is it confined with other buildings? Is it free swinging or whatever? The shape, in this case rectangular, gives us a lot of hints of what kind of type it could be. Also, rectangular building with only few corners have a better shaking behavior than buildings with a lot of corners where the stresses are accumulated. The roof shape is also a nice tool that can help us understanding what kind of epoch this building was built, and this tells us about the overall structure. The processing that we're doing is we update from OpenStreetMap every 60 seconds, and then we process all the changes, and with our rule-based engine, basically get all the building properties that we want. Here's an example of how that looks like. First, the big picture. Here's Luxembourg. If I distribute the buildings according to the built area layer, this global human settlement layer that you usually use, this is what it would look like. Each tile and its color represent a number of buildings. The brighter the color, the more buildings we have. You can obviously see Luxembourg is lit very well, but there are also some artifacts, like the freeway here is also lit. Why? Because its built area is the same signature in the remote sensing. But if we replace this with our buildings, this is what it looks like. You see almost the whole building buildings are collapsing to really the city center. So we have a much better idea of where they are, and we know they're not on the freeways. This is very helpful. To go a little bit into more detail, here's an example from Vesuvius volcano. Up here in Naples, Mount Vesuvius, Pompeii, who was ever there. This is the area. We can put an earthquake on that. This is the shaking intensity of an earthquake that occurred, I don't know, 10, 20 years ago. And so here's the strongness, and obviously the shaking gets lower and lower. And then we have, for instance, historical lava flows or the current flood hazard. And here are the buildings that we put on top. And then you can see there are particular buildings that are very heavily affected by almost everything that can happen there, while others are a bit more lucky. So here you see there's almost no flood hazard, while here, pretty bad idea. Then the blue buildings, for instance, are commercial entities. Here are brown buildings that you probably cannot, no, I can't even see them, so you cannot. But this would tell you that this flood, any flood here, would not destroy the commercial district, but the industrial district is in danger. And so on and so forth. You see there's a lot of detail. But all of these buildings carry more information than just the occupancy, but there's so much I cannot just display it here. Now, this is the beginning. The process then is to use a loss calculation and then compute damage, fatality, or losses for every building separately. Now you could wonder, is this level of detail really necessary? And it really depends on who you are and where you are. For these cows here in Kaikoura, it was very important. They were at the right time on the wrong, at the right place on the wrong time. But also humans are affected by this. So here's an example of the Coquimbo earthquake in Chile, 2015. That earthquake was a subduction zone earthquake away from the city. So the city was first hit by an earthquake. Here's the expected damage, building by building. And then it was hit later by tsunami. And now you can exactly see which buildings were actually affected by the tsunami, which were affected by the earthquake only. And so it makes a difference if this is your house or this is your house. So the specific location, depending on the hazard, is really important. And as soon as we're talking about water, this is super clear cut what is dangerous or not. Here's another example. The Niigata earthquake generated liquefaction. So you see these are all the same buildings, while these here are basically unaffected. They have tumbled completely just because this patch of underground was different than the other. Similar picture in Christchurch, liquefaction again. Here is an area that had these kind of well-saturated sandy soils, and so the water was coming up, while here this is completely different. And again, if your house is here, it's still there. If it was here, there's nothing. The city declared this as being a red zone. Nobody's allowed to put anything here. Another crazy example of side effects. Here's the Armenia earthquake in Colombia, and you see how you can basically draw a line of which building is affected and which isn't. 2016, I visited the Kumamoto area in Japan. You see here the earthquake rupture, and all of these buildings are basically pretty heavily damaged. And here's one building that you see there's basically nothing left. But if you have a map and you know that this is 106 square meters big, then you can immediately have an idea of how many people have probably lived there. And that's important, as you will see in a minute. But this information can help, particularly disaster management. And the other thing is, and this is why in loss assessment or damage assessment, as soon as the earthquake occurs, is important. Here you see two buildings, pretty much the same. This is obviously collapsed, but about this building, it's very difficult to say what it is. It looks okay, it can be okay, but many of these buildings are built in such a way that they are able to withstand structurally the earthquake, but they are afterwards so weakened that they have to be taken down, and then they get these kind of notice that they are unsafe put on that. And this is done by the emergency management. This is the group that were dealing with the Kumamoto earthquake. And for them, and this is why I said that the loss assessment at the beginning is extremely important. What they really need to know is how many shelters do we need right after the earthquake. Because just counting the buildings that are destroyed gives you a completely wrong number, because the other ones, you have to send an engineer. But if you have an idea what's going to happen, you can much better plan into the future. So the model that we are building, or this kind of platform for this data, we have a coverage currently almost all of South America, Africa, and Europe. We are now working on Central America, Middle East, and Southeast Asia, and trying to find more of these engineering information all over the world. But I think US will be next, and we know that for New Zealand we will get something in the next year. So that was me. Now it's about you. What can you do to help us a little bit? We, of course, need building data. Detailed building footprints, that's the first level. We really want to know where the buildings are. Even if you tag a building, yes, it's a huge help because we know a building is where it is. And from there, we can actually get quite a lot of information already because we know the geometry and we can make guesses about the size. Much nicer it is, of course, if you give us hints of what kind of occupancy type this building has. So you can use the building tag, say apartments or offices. You can use a building use tag or POIs. And that helps us very much, particularly to figure out if buildings were built according to the building codes, or what engineering type they actually belong to. And as I mentioned earlier, the number of people that, that stay there per day, per time of the day, so during the day or the night. And of course, the absolute diamond discipline is nice 3D, so we get really an idea of how many stories we have, what's the shape, what's the roof, etc. That helps us way more. And that was my talk, and I'm happy to get some questions.